May I get started? So last time last part, I basically tried to review for you what Griffiths did. I have not figured out the answer why Griffiths was not happy with the discussion of the English result. But basically, he probably think this is not a very good piece of expression, because when rho is 0, the tip stress becomes infinite. He wanted to settle this or attack this problem in a different way. So he used energy, right? So basically he says, oh, you store this much energy. If you let go, I can release that much energy that you stored. And if that energy is enough to pay for the energy required to have a new surface, you should judge that as the condition for crack to grow. So he ended up suggesting, as I was trying to show you, that's how much energy release you can have per unit area. And once that grows, because this thing is increasing with the load, so you can keep loading up, so the energy release rate will keep growing until you have enough to pay for the energy required to have a new surface. So happily, they identified these 2 points, and then, of course, you get this expression in the red box. And that's Griffiths' law, because if you just move A to the other side, take a square of that, so sigma becomes this, right? And that's extremely well known for 100 years of Griffiths' law. And we started to say that at the end of the class, that unlike window glasses, other materials, this operation, no definition. In other words, you keep loading up until some moment fracture occurs. If you measure the stress at that moment, then of course that's that particular critical stress. And this operational definition will tell you how large that GC will be. And for other material, we find it's much larger than gamma. So that's where we were last time. Among other things. So I certainly indicated to you that this is, when this is true, it's no longer a very pretty picture, because what is then GC? It's not, if it's not gamma now. Why you need to release so much more energy, since you only need gamma to form new surface? That's the question. And the answer is not there for a couple of reasons, which is where I suggest that fracture mechanics can be told in a different way, unlike textbooks. This different way is the textbooks. Let me review for you. Basically, textbook, if you read any textbook at all, notice what I did. Last time we introduced the concept of so-called stress intensification factor. It is simply, in our language, defined. Where did I have it defined? Remember, I had it defined as load parameter. I call it K. So basically, K, here it is. K and G are related like that. So when people in the textbook say fracture occurs at G reaching GC, we're also saying K reaching KC. And what is Kc? Kc is exactly, I'm going to ignore the pi that conventionally is in the square root. So let me now stress this point. Open any textbook, we are happy to indicate, man, we have identified something called G. When G goes to GC, fracture occurs. And since we know the operational definition of G, then by definition, you have basically sigma C E, A E as GC. Pretend GC is some magic number, then all of a sudden you have sigma C as 1 over A. In fact, that factor, as I said, is K, and Kc is nothing but E GC. The only unhappy thing is now GC is now gamma. It's whatever I don't know. So frustrating. It doesn't matter in the representation of GC or KC, you're stuck with the beauty that you can claim for many very brittle material, linear elastic brittle material, that there is this magic number. You hit that number by driving up your stress, right? So the G grows until it met some magic point. Boom, it occurs. So let me summarize the difficulties I had. One, what is GC, meaning GC or KC, in the sense of what? Why it is a constant. Why it is a constant? Only if it's a constant, you have this law, right? The KC better be a constant, otherwise you wouldn't have this law. But we found this law holds. Are you with me? Second, the difficulty I had. Second, okay, I still should say why. Why GC is so much larger than gamma. So I said two things. I said, number one, it's really a wonderful thing Griffiths did what he did and discovered there's such a thing called toughness, right? We call this toughness. It has two word names, toughness or so-called critical energy release rate, right? They mean this, rigorously speaking, they mean the same thing. But this two questions left unanswered. So I can, eventually we'll get to the answer, but I can first try to convince you overcome with this question. In fact, overcome is really what we need to do. What happens is if this is true, then we're basically saying that GC is all just dissipative. P stands for plastic. Or how else you can think about it? Why would you need to build up that much energy and release it at the point of fracture? So it's very convenient to think that, you actually, in fact, that's where you shouldn't use energy release rate. You probably should use energy dissipative rate, because somehow the energy is all spent. Why? Because according to this argument that I used a sort of a scaling level to say this much energy did become released. No, it was initially stored. In fact, consider only elastic material is stored elastically, And upon crack moving, it's released, and it released so much so that we are forced to say there must be something involved other than creating the free surfaces, which I remind you last time it's monomeric. Monomeric, meaning monolayer level, the surface part. So what about a simple solution that the energy stored near the fracture surface and released? I say this because we kind of know the answer today now. An answer we knew actually before, but we only recently rediscovered ourselves. What about if this energy and stored and released over an extensive region instead of a monolayer? In other words, so I am. Let me switch to. I created the lecture 17 as a new page. So let me propose that you can think about it this way. It's so convenient, so convenient. So imagine that that's the little crack that will grow, that will move, and it moves when that tip stress reaches the inherent strength. And then you can calculate how much energy will be released. The energy will be simply whatever the energy you stored in the sample during the moment of fracture. And the volume will be basically thickness, a little movement of that, a little movement of that growth of the crack, and then let's imagine what involved stored is not a monolayer but P, something we don't know, P. So that would be how much energy you have on one side. And your dear GC would be that energy per unit area, which is what? Which is delta times. Which is delta times the thickness. So you get what? Basically, you get WF times P. And in the limit of linear viscoelastic material, this energy density is nothing but that integration. Remember I showed you, and therefore it's nothing but 1/2 of sigma epsilon squared, and it's nothing but sigma squared 2E, and often I don't even care about 2. Except this F now is the fracture strength. Yes? Sorry, GC is what we call energy release rate. Gosh. The best way to, yes, is really avoid using E. Oops. And call it U. It's very common in textbook to use U. So I'm not sure I answered your question. Yeah, so basically, if you are to advance delta amount ahead, which means fracture occurred, then you will release this much energy. And it will be released over a surface area of basically this little area. There is a 2, I don't need to add it, right? There are 2 of them. So basically it's the length of that. And so basically it's a rectangle like this, right? Which is delta times t. Sorry, t is not time, it's the thickness as defined here. So I was just trying to do it in a hurry that this quantity that I'm so perplexed by in terms of its magnitude involves energy release of potentially over an area much more than a monolayer. In other words, the P might be much more than the network strand size, for example. It turns out this formalism is something that we will be able to demonstrate. But so here I'm just formulated as if I already knew the answer. The point basically is I want to say that one of the worry can go away if you start to recognize that that the energy stored is not over one monolayer, but energy stored over a, as this cartoon says, over a region, an unknown region of P. But let's get that, let's have that as the starting point. The part I hope we can proceed is really to go to so-called the next section, 3.3C 1.5. This is a crucial part of the discussion in fractional mechanics in some sense. And there I will be very brief, however. So basically, by the time of 1939, Westergaard produced, instead of English, right? English had this. Westergaard produced something it really had it really basically considered an infinitely thin opening, meaning crack. Infinitely, meaning mathematically thin. Zero thickness. Actually, zero thickness. So in that limit, he was able to quickly show that the stress, same story, right? You load it and you try to load it up. The stress at the red point, call it the tip. I always prefer just to call this the tip. He basically claimed that this tip stress will go as the familiar K. That's why I introduced K at that time. And if you like, there's a 2 pi. So K is what? K is sigma square root of A. Let's say twice of the size of the card. The object is infinitely large compared to A. And he produced this result, which you can guess is give you the same trouble the English gives you if you are willing to go to R goes to 0. In other words, as soon as you approach the tip, the stress will diverge, will approach infinity. So this is the famous square root singularity. Now you can start to realize why the square root is everywhere, because the quantity you need to describe your fracture involves a stress and some kind of length scale. And the mathematical structure of why it's a square root of of length instead of something comes precisely from models like this, such as English model. The English model, if I remind you, is this. So that's the English model, a solution. Look how similar they are. Except the English was talking about just the curvature at the tip, whereas in this new mathematical result, we can take R all the way to 0 and cause divergence. So it looks like this is where we see how people made progress. And progress made was by people like Irwin. And the kind of material they're looking at are the metals, which were, as I said, were usually done, something like above BDT, in the sense your steel or whatever could be such that it shows a sense of yielding already. You can Google it, find out how steel breaks. Typically, it breaks in a very rough form, not very sharp. So that involves a little bit of this coming down, and that's yield. Therefore, you are entitled to suggest that there is a lot of plasticity. In fact, Irving simply says something very trivial, that you keep loading, that is when you keep going up, because, in other words, as I move R towards 0, my tip stress goes to infinity. What stops it is there must be a yield stress. Meaning, instead of stress build up to infinity, which is unphysical, it will build up to a length scale where I'm going to ignore the 2 pi's, where, so if we plot it now, the tip stress as function of R, instead of diverging, I know I'm drawing it poorly, but basically a square root minus square root divergence is pretty sharp. Instead of diverging, he would say it will stop at this yield stress. And at what point that length scale, at what point the yield occurs? Well, that's up to the K you have, right? In other words, that scale is nothing but a sigma y K squared, right? So basically, Irwin basically says, infinity is problem solved. It will stop there.
I might have missed it. What did we define R as again?
R?
Like from the Q-tip, K over
R, right? So take the tip as the origin of your coordinate. R is some distance away. That's the R. So it's how far away from the tip. So let me say it. R is distance from the tip. Therefore, R equals 1 is when you are at the tip. Yeah. So did I say 1, 0? I did say 1 because I heard it. Yeah.
So your most recent graph that you did is stress at the tip versus R, but since R is different, the distance from the tip, it would be more accurate to say stress, right? Instead of stress at the tip. Because the stress at the tip is only when R equals 0, as we just discussed.
I'm not sure I follow you. So basically, instead of perceiving that the stress can build up more, you cannot, because the material by that point start to yield. And they perceive or they propose beyond that, the stress just stay at the yield level.
Yeah, what I'm saying is just the label on the y-axis of that graph is sigma sub tip, but the stress
Oh.
is only when r equals 0, and we're looking at
No, you're so right. Are you kidding? Yes. So there got to be. Are you kidding? Are you kidding? So this is our. Yeah. So give another word. So for example, in fact, this is where I made so many omissions. Take one component. So for example, if you are take a coordinate, that's why I'm trying to simplify everything. X, Y, and Z is coming out as the thickness of your sample. Then take any component of that stress. So for example, X, Y. And by the way, I admit I intended to omit all the details. By the way, as asked there, if you have that coordinate, for example, even just look at the XY plane, you have an angle there, right? So there's a function of angle that I'm omitting. I'm just trying to show you the basic features of that solution. In fact, there's an angle, because depending on different angle. So basically, there's a butterfly kind of distribution of stress. Yeah.
And does that also hold true for points along the infinitesimally thin fracture line, or does that?
So the angle could be 0. So
On to the left, are we stress on?
of course, there's no stress here,
No stress.
because it's separate. Yeah. Good point. Yeah.
The R is just like an arbitrary point that we pick anywhere.
Right. R in theory, you can best do it in some spherical coordinate. So there will be a theta. Will be a phi actually, right? Whatever. Yeah. But in fact, let me simplify it. In fact, when it's presented, this is just two-dimensional. So a polar coordinate is what we're talking about. Because it's a sheet, so it's actually, you can simplify it. So you are so right. So it should be this, sigma y. Only the point at the tip is, of course, should be labeled as tip stress. Should be labeled as sigma tip. So you can imagine, depending on different loading, you get a group of lines like this. I know I should use a different color, but basically they all going to stop here. So depending on the load you have, you'll be prescribing a different, what this called. They call it plastic zone. This is an elementary concept. So coming from polymers, I was, of course, a little bit bothered by all this because below BDT, for our polymers, precisely you don't have much plasticity, right? It's brittle. If that's the case, how can I involve a definition of a tip region that's plastic? So I was somewhat find this to be somewhat objectionable, right? So you can see everything is connected. If you really have just an elastic material, such as our rubber, there's no plasticity. It's just a purely elastic material. So it's kind of, I think it's sufficiently confusing. And you can now today realize the confusion is in part related to the difficulty of this being much larger than gamma. So we think it's very permissible or plausible that there's a lot of plasticity. Do you understand it? So I'm just trying to, I think my colleagues may really get mad with me for saying all this, but I'm just an amateur, so I'm okay. In fact, I intend to suggest that I'm teaching fracture mechanics as an amateur. So therefore, I'm free to complain about everything we have seen here. So yeah, it's a bit. I'm asking you. It's a bit weird when you have a brittle, glassy polymer. It doesn't yield, but you are forced to introduce the concept of yield. Yeah.
So I just wanted to ask a question about the plastic zone. We usually refer to plastic as after the yield.
Exactly.
It looks like I just wanted to make sure I understood that graph. So you're saying if you have a different load stress that you're going at, you get a different curve, and plastic zone is always the RP is always the same, or?
No. It's. I must have done it wrong. No, hold on. I must have flipped it, or I can use a -2 there. K must be on the top. So it grows with K quadratically. Just by necessity, because they think this thing can be so sharp, it will always reach sigma y. And the region just enlarges. And I scratch my head like no tomorrow. And then what? No failure because you have a plastic zone. But then they magically says, look at this expression. And carry this expression to the point of fracture. What happens? K goes to Kc. These symbols are all in the textbook. And the plastic zone grows to this magic size called RP star. And magically, when you grow that much, fracture occurs. Why not earlier? I don't understand. Why? Yeah.
The part I want to get clear on is, so you said that because the stress is in reference to the tip, it doesn't seem like it's symmetric around this fracture. So why, if you have an R distance away in the direction of the fracture, then it's going to be a very low.
It will be symmetric with respect to the fracture plane. Yes, 30 degree this way or 30 degree that way would be identical.
But it won't be with the other tip. So
what is the other tip? You mean other side?
Yeah.
Oh, look, one side, you're too busy. Look, one side is good enough, right, for us. So on that side is symmetric too, right? But you just draw that way. Why you bother?
Yeah, but how does it meet in the middle? Like yeah, I get in that, so in the direction.
So the discussion here will be identical to the discussion on the side. Yeah.
But beyond 90 degrees, how does the behavior?
You mean all here?
Yes.
Well, except the fact that the stress won't be very large, so why we bother? We only look at where the stress is highest, right?
Okay.
That's the point. Because that's where the fracture is happening, right? Presumably, yeah. So this is frustrating, but then let me tell you the good news. This is frustrating, and then you see that the reason it occurs is because this solution prescribes infinite stress. So you need to cut it off, set a cutoff, and that's how this is all argued. But in doing so, it involves plasticity, which is really nasty if you don't have plasticity. I keep insisting when you have a piece of rubber, there is no plasticity. You're way above TG. Meaning, I think this concept is so deep, it's not funny. Plasticity goes in hand with concept of yield, right? So there is a yield point. The yield goes with what I initially said to you guys. What is viscoelasticity? It's a transient structure that produces elasticity that lives on finite time. In other words, yield always means structure is broken. In the glassy polymer case, of course, that breaking is about whether you activated enough of these, breaking enough of these covalent bonds so you have yield and plastic flow, so-called. Once you are way above TG, that interchain interactions are negligibly small. They are just the only structure you have for you to worry in the case of elastomers is whether chains are breaking or not. So if chain is not breaking of your network, then where do I assign a plastic zone here? I can't, really. So let me get you the help we need. Of course, I will show you I'm doing it in a sequence that's not chronological, meaning it's not what has happened in history, meaning a history of only a few years, 4 or 5 years. That is, we later, after learning our results from my experiment, which I have yet to give you any sense of what that is, but will soon. We learned that there is such a thing called Creager-Paris solution, published in 1967. Hardly ever acknowledged in any textbook. There could be 1 or 2 you can find, but out of a dozen or more, you don't find it. And it answers all much of the puzzle, and in fact merges with what you see here from English solution result. Let me review the English solution. The English solution says if this is your tip, then the stress is enhanced by this factor, right? So rho can be written as B over A. So basically, that's English. And by the way, as long as rho is not 0, this formula survives. So there is no infinity. And of course, you can ask. Maybe this is the time I should ask. Carry out this English solution. Let me ask you, how do you perceive the moment of a fracture? Let me rephrase it. You got the sample. It's being stretched out, so that the stress is growing as you stretch more and more. Right? Until when would fracture occur? So this sigma is keep growing, which means your tip stress is keep growing. Until what moment? Yeah?
Would it be, would it start at the yield point? Or
Well, if there's no yield, it's a good point. If there's no yield, then until what point? Until the stress here reaches what? Exactly. But by saying so, by saying it, you have already basically proposed that there is a fracture mechanism, right? The mechanism being local stress reaching inherent stress is when fracture occurs. Or the crack start to propagate. right? This is non-controversial. All the pioneers admit that this could be the way to think about fracture. But what's strange to me is the textbook doesn't explore this point of carry this English result to the point of fracture. So on the left side, this becomes sigma F inherent, right? On the right, sigma become what? What do you call that? The load. What symbol we used? Huh? Sorry, meaning that stress load, we say we reach a point, boom, fracture occurs. Yeah. No, what? Sigma what? So, yeah, so there is a question of so-called notations. Sigma B is reserved for notch-free materials. This is one that has a notch. Doesn't matter on the edge, or anywhere. When fracture occurs, we call that point what? The sigma C we have been talking about for so long. Everywhere, sigma C. The only place it becomes sigma B is we trying to predict using this framework to suggest what is the nominal strength involving the flaw size. Right? Clear, right? So it's basically when you have an intangible cause, it's a sigma C. We call the critical stress. Okay, so let me write it. Don't you right away see something? Fracture strength is sigma C A rho A square, so a square root of rho. What is this? What is this? That's Kc. Didn't I previously what is Kc? Well, that's the operational definition of Kc. But didn't I just previously told you that I don't know when you say K goes to Kc, it means what? Because Kc is just operationally given. I don't know what that means. But now, do you know what it means now? When G is going to Gc, which is actually a little easier problem because in linear elastic region, they are just related, quadratically related. But do you see what's surprising here? What do you find? This is your Kc by identification. And therefore what? Therefore the English solution says what?
One has square root of A on the bottom, one has square root of rho, right?
I'm merely asking you to just clean up and write this again. Yeah? I'm not looking at my screen. I try not to. Not so bad. Is it not? Sometimes you just think too complicatedly.
Well, earlier with the Westergaard solution, you had K equals sigma times A.
Yes, go ahead. You are talking about English solution? What are you trying to say? Here? Don't need to go any further. This is the English solution here. Sometimes I need a mouse or something. This is the English solution. I just don't want to mess up this. Right? This is the English solution. And we carry this English solution to the point of fracture using this concept of what fracture means. So I'm right. It's just like the way we work out anything. Left-hand side, they let it go. Right-hand side, they let it increase. And we agreed at fracture, this side become, meaning is when it reaches inherent strength. This side is conventionally, we call that critical load. So this is just a rewriting of English solution. Doesn't English solution support, sorry, apologize. Doesn't the English solution support Griffith's law? Yes and no. Meaning, this is KC. So what happens is I was complaining forever that I don't know what determines this KC. I just don't know what happened. And you guys know now what determines KC. Yeah? Jesus. Any trouble with that? Is this not an aha moment? Or shouldn't I teach fracture mechanics in a hurry by showing this?
If you want to know the truth, it might become more of an aha moment when I actually sit down to write the study guide on this.
Review it a couple times.
Yeah.
Yeah, so it only means the difference between a 23 years old graduate student and a 60-year-old graduate student. So when I learned it, it stopped me. It stopped me. Give me this, where is it? Give me this GC goes K equal to KC, G equal to GC. It stopped me because I don't get it. What is that? Let me try to give you a different side of the question. Remember, G was Griffith's argument that how much energy can release. Okay, we empirically observe when we define and measure G in this way, we find this G reaching some magic number, let's call GC, boom, fracture occurs. As if you must have this much of energy release at the moment of fracture, yeah? And similarly with K. It's probably more obvious for us. With K, K is defined as sigma times A. Magically, there will be a moment fracture occurred when, of course, this is true. I indeed experimentally can access that magic sigma c. But why that magic sigma c? Why not something else? Meaning, why it's 10 megapascal? Why it's not 20 megapascal? Similarly, G goes to GC. Since it's much larger than gamma, then I don't understand why it need to be that particular gamma C, GC. Okay, so sounds like it only bothered me.
I think we don't have enough emotional attachment to the problem to be so.
No, I didn't have emotional attachment, Charles. I had zero emotional attachment when I was looking at it. It bothered me. I told you I couldn't. I lose sleep. I just wake up earlier than normal after hearing this. And I merely suggest now I know the answer. I can sleep. Jesus Christ! Oh Lord! It's an aha moment. You got two alternative expressions for the same quantity. One is operational, that you go to the lab, close your eyes, you can get it. The other, you have to scratch your head and think about prescribing what is the inherent strength. And that's nasty. Who wants to do that? Perhaps that's the reason we didn't care. Let me rephrase it. I learned, a teacher proudly teaches me that, which is, by the way, a remarkable achievement. The fact G is the essence, and because linear fraction mechanics, they are strictly related in this way. All textbook says they are equivalent, so there's a way also to think about in K. It's fine. You go to the lab, you get Kc measured. And Kc and Gc, they are, my notes is all mess. They are used to rank material. That's what we are so proud of. I don't care what is Gc. I know this material has a higher Gc than that material. Isn't that sufficient? Isn't that sufficient? I think it is.
So the question would be, I still don't understand. I guess I don't understand if there might be like a physical way to explain the K parameter. Like I can see here that there's like an expression, but if you might have like what K physically besides a constant to describe our material.
There is. So ever since in the entire literature, this English solution tells you what K is. It dictates how massively stress builds up toward infinite. Look, there are K. This is where I kind of start to tease you guys. The beauty of mathematics is once you write it down, it has all the meanings there is. I have nothing further to add on to it. Look, that expression tells you what Kc means. It tells you the intensity of the stress buildup. Yeah? And it has that particular definition out of that mathematical solution. But of course, that mathematical solution involving K, as I remind you, the English also involve that mathematical. The English also involve that K, right? I said it, it's in the previous one. So that's K, that's English. So let's take a break. Maybe we could even, I could even hear a couple of, just resume. And so, oops. English, we just realized it solved my frustration. Because previously let me dramatize it, okay? Previously, I only know Kc is given by this on the left, yeah? Operational definition. Now, the English solution tells me it's given by the inherent strength times the radius of that ellipse at the tip. Since it's linear elastic material, I actually further know Gc is Kc squared divided by by E, which means what? It's sigma F squared E rho coming out of the square root. What is that? Isn't that my little WF? The fracture, or the so-called work of fracture. Basically, it's the energy storage per unit volume involving the stress to the level of inherent strength. The rest is rho. Isn't that what I just started? Remember, I was eager to show you this result that I dreamed up? Because I know that answer. So that P is my rho. And we know this quantity through experiment. That's a future I will discuss. But now you start to see two things. Operationally, again, I call it. So let me be absolutely clear on this. I just cannot imagine nothing emotional. It's just reality. There are two pairs for the same quantity, either Kc or Gc. Which two pairs? Your experimentally accessible stress and cast size and your materialistic quantities of stress and length scale. And same involved here. You either have this pair or you have that pair. Arranged in different ways, right? One has square, one the other doesn't. Who cares? In fact, they are quadratically related, aside from Young's modulus. So the beauty was that both Kc. I don't get enough strong reactions from the establishment. That's where I'm frustrated, actually. So this is written into the perspective article. So this thing is given by two pairs. As I keep saying, it's given by two pairs. And this pair involved the materials and involved the geometry of the tip. And how do you determine that? It comes naturally. So this rho is also material dependent. So you got operational definition one side. I can call this materialistic definition on the other side. And it's all in English already. Okay, let's continue. So what we learned? What we learned is that, obviously, that the strength of your material and the shape of that notch shape, in the sense of curvature, would prescribe the value for K, as well as for G. So that's remarkable. The only thing left is how come you got this rho, this particular curvature. Or what's the size of that curvature? Meaning, is this molecular? Or is this microns? Or this is 10 microns? Or is this 100 microns? Or whatever. Down to earth kind of question about, because all this is abstract mathematics, right? It doesn't apply to, and it refers to any material. But that's the beauty of it. So that's why I want to finish just a tiny presentation of the so-called Creager-Paris solution, which is a tiny extension of beyond this English result. Basically, they want to answer the question, not just what is at the tip, which is the English solution, but as you see, what is slightly away from the tip. So the way they must be, so Paris is very famous actually in the field. So the way they constructed it is clever to avoid any trouble, to avoid you running into any trouble with singularity. So they choose a origin of the coordinate about half rho inside. Okay? So the R approaching the tip can only be half rho. Get it? Right? So R cannot be 0 when you approach the tip. And that does it. So basically, the stress now as a function of R, you can again talk about this component, stress, is essentially still K and still R, except R doesn't go to 0 anymore. And there will be an additional term that's 1 rho 1 over R. So that's the solution in the front direction, theta equals 0 direction, which is the English direction, right? Because English was just talking about that point. Now this result, of course, collapsed to the English result. Yes. Where you want to go? Yeah. So it not only converts to the English result, and there's no divergence, straight arm. Treat it as a face value. He's considering a linear elastic material, which is fine. I insist your PMMA well below TG is such a material. And also, I should add, very strain intolerant. In other words, this treatment is all done in the limit. Sometimes it's hard to speak and write at the same time. So it only works if all this happens within a few %, which is fine, again, for your PMMA. So you have, right, I said it, no divergence, no stress divergence. And convergence to English, this result. And of course, as good or better than English, right? Because it has everything that it has. More importantly, if you look at this mathematics in detail, as a function of r all the way goes to 0. Oh, sorry, all the way goes to the tip, which is rho 1/2. Or you can do it differently. You can plot as this so that this goes to 0. Yeah, fair? Oh, sorry. Basically, 0 is when you are at the tip. When you do that, you'll find, again, this thing quickly builds up as square root of r, but necessarily saturated to the English value, because the English value is at r is at this point of 0. Yeah? Notice what feature you notice here. Well, first of all, it doesn't go to infinity. And this is the really extension of English, right? English could only speak about this one point. And now he can speak about any point beyond that point and show the stress built to there. But what's instructive for us? It's not a plastic zone, but it is a zone where the stress starts to saturate, meaning it no longer grows as fast as 1/r, for example. So that's just a mathematical feature of it. So let me see if I had it here. I opened it already, I recall. So by the way, I have actually uploaded all these 3 chapters on fracture mechanics. And since I have it here, let me show you the celebrated, I think, the Creager-Paris solution. So that's the solution. It's mathematical and has also different angles. And this is how it looked like, gently plotted. So if you plot this as log scale, or plot it as 1/r, normalize it. Basically, there is a region stress stop growing. And this particular one was plotted as minus 1 square root of this quantity goes to infinite is when you reach the tip. And you can see, again, before reaching the tip, the stress stop building. Yeah? The tip is at r equals 1/ρ/2 by construction. Yeah.
So you're saying if you plug r equals ρ/2 into the equation there, that's their result, you get Inglis's result.
That's the what result?
If I'm not mistaken, what you're trying to say is if you plug r equals ρ/2 into that equation for signal y, you get back the English result.
Yes, absolutely. As I said repeatedly, it converges to the English result identically. Yes. Yes, yes. So it has to be, otherwise it would be a wrong solution. Yeah.
And on that, I guess, so I've been thinking, since you said that rho was curvature, as I recall, the default units of curvature are going to be like an inverse unit because it's
curvature of radius of curvature is a length.
But curvature.
Radius of curvature. Radius of curvature. If I say curvature, I only loosely say it's related to the curvature of the tip. You are completely right. Mathematically, curvature usually the reciprocal of radius of curvature.
That's why I was like
yeah, it has the dimension of length. So yeah, so which we have defined even for English. The English here, b squared divided by a. So it has dimension of length. Yeah. So what's left? what's left is probably you can stop complaining about stress divergence. Just give me a flaw and a tip that has a radius curvature of rho. I should observe this behavior. One, stress doesn't shoot through the roof. And we know the stress can never be higher than the inherent strength, because that's the moment fracture would occur. And we just went through this lovely result from English. And number two, not only is limited to that level, but over a region of that level, this is a crucial comment now. Over a region that is on the order of a fraction. I hate to use in fact, you know exactly where it is, because I have the exact point of where it starts to saturate. So let me spend a minute on this. So for example, if you plot this R normalized by square root, by 1/2 rho, you minus 1, which means 0 is when you're reaching the tip, okay? And 0 in log scale, you have to plot infinite orders, so I don't have to, I just plot 2 orders, so it's -2. So basically you can see that the stress starts to saturate at about a few tenths of the rho, okay? Beyond that, they all have the same stress level. That's the concept. So all I'm trying to say is, look at the mathematics of it, you realize there is a region where stress is pretty high. That's all I'm trying to say. Pretty high compared to the tip stress. And that region, how much is? Yeah, so let me casually say it's about 1/8 of rho. So at least 1/8 of rho will have high stress. Which means you store high energy in that region. Which means if rho is not monolayer on scale, but much larger, then you have a huge region where where energy is stored. So it turns out after a couple of years, we find the entire mystery of linear elastic fracture mechanics is in the origin of rho. What is rho? Now it's a little bit more subtle than I wish it to be. It simply is subtle. In the following sense. Now we can come to Earth. This is the theoretical result. It has pretty important, it contains pretty important information. Now come back to Earth. You go ahead, go to your lab, and you try to make a notch, the English kind of notch. That's hard to do. But basically you can, on the side, try to introduce a notch into your sample. It could be a rubber too. And you now realize what you have been doing. You are preparing a crack like this with a tip. Can you control how sharp that tip is? Yes and no. That sharpness of the tip is up to the material to respond to how you are cutting it, right? How you are introducing it. So there is the possibility, whatever the crack you introduced in your PMMA is such that rho could be, who knows? Knowing today what we know, I can tell you, or you can be convinced, if I try to make such a crack in window glasses, do you expect that tip of that crack to be very sharp? Short answer is yes. In fact, it might be, through calculations, whatever, it's about as sharp as 1 nanometer. It's still not 0. So this whole framework of English carries through. And for our polymers, would it be lovely if it's in the micron range? Well, lovely. It's actually puzzling if it's in the micron range. And if it's 100 microns, then it's more than puzzling. Then it first shows the physics is not a monolayer problem. You're storing energy over a huge scale. And that would explain why GC is so large. By what? By the notion that this P is very large. It's not a monolayer. When you reduce that P to 1 monolayer, that's surface tension. But if this thing inherently involves a geometry that allows energy to store over a fraction of rho, and rho is not monolayer, we just acknowledge for window glasses, it might be just a monolayer. Because those bonds are so short-ranged and connected. And our dear polymer, my goodness, they are connected over such large scales, so soft, and so much freedom, that it may not be unreasonable to think that this tip is never sharp. So unless you beg for some homework, I was planning to not send you any homework anymore. But a lovely homework would be exactly this English result for your window glass. Now we can really plug them in and appreciate everything. If I didn't say it, I say it now. The fraction mechanics started with worrying about window glasses. It tend to have a strength nominal, right? So allow me to rewrite this English result by a different notation that we are not to be confused. We treat this glass as having flaws of size RA, and then this sigma C is B now, right? Because we're just perceiving there are some flaws of A, and we're trying to break it at nominal strength of B, sigma B. We reserve that notation for it. So that's about 200 for window glasses. And we learned that the strength of the theoretical strength of the window glass is about 1/10 of Young's modulus, which is about 7 gigapascals. The rest is out there. I once offered you that your window glasses probably have defects on the order of 1 micron. Now I offer you the information your rho is something on the order of 1 nanometers. give and take. And, or could, now it's up to you there are two unknowns to have this differ by a factor of 100. I just need this. I just need this to be 100, right? Yeah. Or I just need this to be 10,000, right? That's all. What? That's homework I already did for you. God. I'm just saying it's this kind of homework that you should be doing, yeah. So to gain some feeling about the magic of such a sophisticated subject called fractal mechanics. So if you don't like this, give you 10 microns, rho is probably only 0.3 nanometers. Basically the bond size level of your window glasses. So anything of a micron, a flaw of some kind, will weaken your window glasses. By the same token, now it's homework. Do the same for polymers. In fact, do the homework for polymer in the following sense. What if they are comparable? See, here it probably is a little bit confusing now. If they are comparable, I claim then you should not worry about flaws. By definition, do you understand the conceptual definition? Because flaw is what weakens the material. If you say, gee, my material is not weakened, then there is no flaw, then you cannot use this formula, right? Or, let me just complete that concept for you. Or, if your flaw size is even smaller than the sharpness of your tip, then there's no amplification of stress. No amplification, no intensification or concentration of stress. Because your intensification is always given by this ratio.
Well, because then that's basically like a vertical stress, right?
Well, I think this is where you don't want to be confused about.
Like it's a vertical form.
What I'm trying to suggest is, for example, if your rho is as big as 100 microns, then you will need flaws at least of larger than 100 micron for the flaw to weaken your material. That you get it, right? But I look at my sample, I don't have anything that's 100 microns flaws. So you're treating this problem in multiple ways. You basically if flaw weakens your material, your flaw size must be larger than this rho is all the, let me write it down. Rho is all the mystery of fractal mechanics. And I haven't solved that myself. It basically is a material response to how failure can occur as they develop a crack. So I'm being theoretical now. I'm saying, hey, if somehow for the physics we don't know if rho is 300 microns, I hope you are convinced by English result, then your flaw must be much larger than 300 microns for you to have the English stress intensification. And I'm saying when I examine my sample, I don't see any flaws that's much larger than 0.3 millimeters. Remember, the here is 50 microns. I keep reminding you, right? So now you start to connect that if rho is 300 microns, then I can already conclude your measurement is free of any influence of flaws because I don't see flaws. Or flaws need to be of size larger than 300 microns to weaken my material, which I don't see. So therefore, I conclude my sample is not a fractal mechanical phenomenon when I break it. When I break it, I essentially see somehow my material reach the inherent strength somewhere, not around some flaws. So properly, we can now come back to the origin, or to why that parcel of did I write that two parcels somewhere? That was not. I didn't write it. Let me rewrite it like this. That why this is true, and why this is a constant, and what determines the magnitude of GC. These are three questions that bothered me, right? I mentioned about it, right? And that's not going to get you anywhere. If that's, you can worry forever about it. So how we got ourselves started? We got ourselves started with the speculation that this may be comparable to the inherent strength. That's where we start. And we had that lovely theory that says, relative to the fiber limit, it could be lower by a factor of 100, because these two factors could be each a tenth. Back to polymer physics. Right? Still recall that, right? That's the idea that we had a calculation, or we had the whole picture that this network could fall apart by bearing how much load? By bearing the load that caused the chain start to pull out. But I also confess to you this prefactor of 1/10 here, another 10th there, is something we don't know. So we only had the speculation that you experimentally observe 50 megapascals. It's possible your inherent strength is also only just 50 megapascals. But we don't know. In other words, the problem you have is what you have. The problem you have is not this problem that has flaws in weakening your PMMA, right? So that's the speculation, or that's the question. That this is probably the scenario, this is not true. True or not is important because when it's not true, you don't invite fraction mechanics to tell you why the strength it is. Well, you better have a way to think about why that inherent strength is what it is. Meaning, it's not affected by flaws because there are no flaws of any sizable, any size that can enhance the stress locally, okay? Strength there. Oh, yeah, I don't know if I made myself clear enough or not. But all I'm trying to say is right, is that the fraction mechanics was beautifully established because we suspect that we can still use fraction mechanics to explain the nominal strength by making an intentional card and measure GC so that I can plug that GC to here to describe inherent strength. Sorry, to describe this nominal strength. But here's the trouble in this whole presentation. What is the flaw size A star? How do you prescribe it? And you make some guess, or you inspect, or what do you do? Huh? What do you do? It will be unique to material, but how? I already labored here because Barry is the first one to take a PMMA and made a measurement. Lo and behold, he did find that Griffith's law works, which says nothing about whether there should be flaws for this cut-free sample. But that's the spirit. You use this GC, come back, try to predict a cut-free sample, why the strength, or explain why the strength is 50. And the way you explain the strength 50 must involve speculating about the size of the flaw, by definition, yeah? That you get, right? A star. And by the way, if you take a sample without any intentional notch, and you make 100 of them, and you find that sigma b varies widely, let's say by a factor of 10, all right? By a factor of 10. And usually people think this is a hint your material is flaw infected. Flaw infected, meaning flaw dictated. Because that variation speaks about the fact that 100 samples have different flaw sizes. So generally, it's not wrong to think if sigma b it varies 10 times or even more. Window glass does that. Then you may start to suspect something. In our dear polymers, granted, there can never be everything perfect, right? There could be dust in your, the way you prepare it. But that spread of sigma b, 20%, 30%, well, let it be, even 100%, so what? And of course, the mystery could be that 100% is because simply this piece somehow is just had a little more better build of the network, whatever, so it's stronger or not. That's not a question. So I'm running out of time, so let me give you the last piece of information that's most curious. We're speaking about speculating the size of the size of the flaw. It's known, or you can patiently go ahead and do this. You make cut of different size. Remember, it should be, if it's double log, it should be 1 over the square root, so it's minus 1/2. The smaller you start to make your flaw, meaning the notch, the stronger your material is now, right? Sigma C. That's just Griffith's law. That's just Griffith's law here. And what they find is this. What does that mean? When the notch is sufficiently small, it's the same as without notch. Right? That's the reasonable logic. And then you know how big this scale is? It's outrageous. It's about 1 millimeter for polystyrene. And you are forced to conclude that your polystyrene has flaws 1 millimeter large. You're laughing because, in fact, by inspection, of course, you don't see a millimeter. And they have actually repeated in the textbook saying, oh, the flaw would emerge to become as big as 1 millimeter. My goodness. In order to fit the framework of the fractional mechanics discussion of the nature of the nominal strength of your polymer, or explain this result. So I know I'm running out of time, but let me give you something to contemplate. What if this implies that your rho is about 1 millimeter? In other words, when you make a cut as small as a millimeter, it's so blunt, the tip. The tip is as blunt as having a radius of curvature of 1 millimeter. Can it still enhance stress? No, it doesn't enhance. It doesn't concentrate stress anymore. And that's why it's the same as not making a cut. Yeah?
Two questions. Just make sure I understand. The linear regional slope minus 1 half when it starts to obey Griffith's.
That's Griffith's, when the cut is very large.
That's when the cut starts to affect the critical stress. And then another thing, when is this homework due? Because I remember.
Which homework?
A homework about, you did the homework for the silica glass, but you also told us to find the case.
It looked like I'm doing it for you again. I'm just kind of joking, right? So basically, the homework is to digest this part of the discussion. Basically, yeah, I think that's what I really mean, right? Meaning, tie the knot, connect the dots here in the sense. I in a hurry offered you all this very classical information. That it, if you have a piece of brittle, glassy polymer, go ahead, make a big enough cut, you will get Griffiths. That doesn't contradict anything like GC being larger, much larger than gamma. That's a totally separate question, right? That you understand. And we also talk about why GC is much larger than gamma, because rho is so large. And then here comes the rho, that when your size is small enough, it's as strong, meaning the cut size, we call it cut or notch size. That's because there's no intensification of the crack you introduced, because the crack is so blunted. And that bluntness didn't I say that bluntness is the mystery of the entire fractional mechanics. We don't know why it's so blunted. I'm just offering what is in Kinloch's book. It's in chapter 7. They start to talk about this. Chapter 3 is on the just a overview of fraction mechanics. And 8 or whichever one was on rubber, which we will talk about in the future. But so when we come back, I know run out of time. When we come back, the real question is, how do we know that this is true? And that connects with everything else, that you blame flaws or you shouldn't blame flaws. The reason you don't blame flaws, which is what? The reason you don't blame flaws? The rho is 1 millimeter. And don't ask me. I mean, we have to ask God to find out. We don't know why it's doing that. But it's progress in the sense we at least know this is how it happens. Okay, so we'll come back and really focusing a little bit more on the experimental side now. As I said, all this motivation or discussion is presented in a way because we already know the answer. Since we already know the answer, we can teach it differently. That's all I'm trying to say. Okay.